So greetings to you all. Nhlengani, that's what we say in our language for greetings. My name is Nhlengani Baloyi. I am currently doing my master's at the University of South Africa. My topic today is going to be covering using machine learning algorithms in a means to ultimately detect star clusters in Gaia Data. There are going to be a lot of redundancies in what I'm going to present right now, precisely because a lot of my points were covered by the previous speaker. So yeah, my job's going to be made somewhat easier in that regard. So just to give a general brief as to what the talk is going to cover, I'm going to introduce star clusters, just talk about some of their general properties, give an overview of the Gaia mission, although we can just skip that because she's already talked a lot about those things. And then talk specifically about some of the actual machine learning algorithms that I use in my research in a means to ultimately detect star clusters. So yeah, let's get going. So we know that star clusters are indeed the building blocks of many galaxies, precisely because star clusters are where most stars tend to be born before they dissolve into the general galactic disk. They're typically defined by being objects, or well, I should say groups of stars that are bound by self-gravitation, right? We have two different varieties of those, of course. We've got globular clusters, we've got open clusters, which are characterized in their differences as being dense, spheroidal, and being packed full of stars in the event of globular clusters. And then in the case of open clusters, they tend to be loosely bound. So they also have big differences in the context of where they're found. So if you guys look at the blue points, those points signify where the open clusters are, where the globular clusters are typically found, which are very, very close to the galactic bulge and somewhat dispersed all the way throughout the galactic halo. In the event of open clusters, many of them are well constrained within the galactic thin disk. So this gives us, of course, a general sense of if we want to find these star clusters, where exactly are we to look? So this is just a quick little histogram plot of just some of the differences in the radii. I'm not sure if you guys can actually see the text there, but if you look at the limits of the differences in the radii, there's almost an order of magnitude difference between globular clusters, which tend to be smaller in the sky, and open clusters, which tend to be larger. And I assume that that has to do not just because of the fact that globular clusters are really dense, but that they also tend to be found much further away from the sun relative to globular clusters. I mean, open clusters, sorry. So just some nice little examples of how these things actually look in image data. So this is a globular cluster. This is an open cluster, right? As you can see, it's characterized by these very bright stars that are fairly closely packed together. And in the typical sense, what people would often do in order to detect these star clusters would be to just perform these very simple star counts, where they would use software like IRAF in a means to essentially just count, like one by one, the stars in image data, photometric data. Later on, with more advanced surveys, tracking, of course, the motion of stars, that allowed us, or allowed many astronomers before us, to essentially characterize the kinematic properties of these of these objects. Okay, and this is just an example. This is similar to what the previous speaker had shown. So in the context of this particular cluster, which is a globular cluster, what you see is this really large proper motion dispersion relative to the background. These are just two different data sets. And then just this is an example in Gaia. So again, these are both globular clusters. And those bright points right here and right here are the ones that ultimately characterize the the clusters, right? Or at least I should say that the motion of the clusters relative to the whole background there. Okay. The importance of star clusters was something that was covered by the previous speaker, but just quickly, if we want to talk about star formation history, star formation mechanisms, if we want to study the history of the galaxy as a whole, if we want to, for example, characterize the mass of the galaxy, we use star clusters in this regard, as they are found, as I said, in the case of open clusters dispersed in the galactic disk, and in the case of globular clusters in the galactic halo as well. So if you want to, for example, constrain things like dark matter models, you can, of course, use globular clusters. And then in recent years, with the almost explosion of these data mining, machine learning techniques in this particular task of detecting these star clusters, a tremendous amount of research has been done, and all of that has been facilitated by Gaia and Gaia Data. So one example of this was a situation where, I want to say, in 2003, it was essentially, I should say, found that the survey of open clusters within a distance of 2 kiloparsecs of the sun was thought to be complete, but many authors since, in the last 5 years, have been able to detect star clusters within that particular distance of the sun, which likely indicates that there's a lot more to learn. So just, I'm going to skip through the just overview of Gaia. Just quickly just say that the main functions are astrometry, which is just tracking the position of stars, photometry, which is just looking at the light coming from objects, and as well as a spectroscopy, which involves just taking the spectra of those particular objects. Gaia being a game changer in the sense that it introduced micro-arcsecond precision in astrometric measurements, and yeah, this was all extensively covered in the previous talk. So, and then some science highlights. We have, sorry about that. So a few thousand new open clusters have been detected in the last few years, in the last 5 years. Many of these particular discoveries were fueled by two things. Number one, it was the use of HR diagrams as described before, and number two, specifically the use of clustering machine learning algorithms, much like DBScan, as the previous author described. And then a few other things like studying YSOs, which are young stellar objects, star-forming regions, as well as stellar substructures. Sorry. Okay. So where does machine learning fit into all of this? Of course, many innovations, as I just said, have been made in the regard of actually detecting new star clusters. And also the sheer volume of the data that Gaia ultimately has been able to survey is such that you need these machine learning algorithms in a means to ultimately I suppose, process the data and do meaningful science therewith. So, just going to the, I suppose, the meat of the talk. So my focus was on specifically detecting globular clusters. Open clusters are significantly more numerous and much easier to find. As I said before, current approaches are largely based around using HR diagrams, but because the proper motions better characterize globular clusters in the sense that they have larger dispersions, it makes sense then to use them as part of the learning process when you then apply these machine learning algorithms. So what is it that we need if we were to actually go about the task of trying to find star clusters? We would need to first pre-process the data, right? So pack it up into some, or at least transform it into some meaningful, transform it in such a way that it is meaningful to work with. Choose an appropriate clustering algorithm that would allow us to characterize the difference between the background and, of course, the clusters that we are trying to find. And then you would then, besides that, use some kind of supervised learning algorithm that would allow you to distinguish between actual clusters and statistical overdensities. Because when you do apply a clustering algorithm, what tends to happen is you tend to pick up things that are not necessarily clusters in themselves, and so you need a way to ultimately distinguish between what is real and what isn't. Okay. So this is an example of the, I suppose, process that was implemented by a few authors, I think 5 years ago. They've been using the same process over the past 5 years, with the only real difference being that instead of using an applied neural network, they use a convolutional neural network. I'll describe what the differences are later. But sorry about that. Yeah, that's really all there is to it. Okay, so in terms of pre-processing the data, the very, very important, should I say, aspects of the data that you would want to select for are indeed the positional data, so either galactic longitude or right ascension, parallax, proper motion, and then of course if you want to go down the route of photometric studies, then you would use the color associated with the blue and red photometer, as well as the photometric G-band magnitude, which, if I'm not mistaken, characterizes wavelengths between 300 nanometers and 1,100 nanometers, something along those lines. Okay, so in terms of my particular process, so what I did was I essentially chose stars with a signal-to-noise ratio of about 5. What this does also really nicely is that Gaia has this weird tendency of negative parallaxes, which usually are linked to things like QSOs, or quasi-stellar objects, quasars. So by picking a parallax over error that is above 5, you essentially eliminate those particular objects. Also, just imposing limits on the magnitudes that are used, 3 being the bright limit of the survey. The actual faint limit, I think, is 21, but 19 is where the completeness of the survey starts to completely, well, I shouldn't say completely, but it starts to fall sharply, okay? For the just general demonstration of what it is that I'm presenting to you, I just wanted to, well, I shouldn't say, the specific way in which I will be going about doing the clustering will be by essentially dividing the data into these degree squared areas, right? The reason for degree square areas is because if we looked previously at the earlier slides involving the radii of clusters, what we typically find is that clusters do not go above 0.1 in the case 0.1 degrees in the case of globular clusters, and they don't go above 1 in the case of open clusters. So using a degree square partition of 1 degree is really good at actually being able to detect both open and globular clusters. But as I said, I'm going to be focusing more specifically on globular clusters. Right. There's also something that is really annoying about using things like dbScan. So the performance of the algorithm ultimately depends on the specific hyperparameters that you use for that algorithm, I guess, right? So dbScan has 2 hyperparameters. One is min points, the other one is epsilon. And the interpretation of these points is that one characterizes so the min points together with epsilon characterize regions within your data that correspond to dense areas, right? And it is the interaction of these dense areas that are of radius epsilon that contain min points number values that ultimately lead to this construction of larger and larger clusters, right? Okay. So the process that I use is one that is outlined in the study that I mentioned before with the flow chart. The only real difference that I brought to the table was in the min points optimization. So what they did in that study was that they essentially simulated the entire data set in order to detect essentially like synthetic clusters that they put there within this new synthetic data set. What I did instead was I ultimately looked at, for each let me put it this way. For each candidate min points value, what I tried to do was I tried to characterize for that min points value some associated radius epsilon, okay? And then looked at, so for each of those candidate min points values, when you sketch the min points, when you sketch the curve of these characteristic distances as a function of these candidate min points values, what you find is that there is a point within this curve where these differences start to level off. And the idea is that that point in the curve would imply or would demonstrate in some way the beginning of the background, if you will, right? The point where you start to use min points values that are so high that you start picking up only the background and not really the finer structures in the data. So this is something that I wanted to mention. And then I talked about this, so we can just skip through this, right? So now after having applied dbScan, you then need to ultimately sort between these clusters. And part of how you do this is by using a supervised learning algorithm, much like an artificial neural network. So this artificial neural network essentially aims to replicate the process of learning within the human, or within animal brain, I should say broadly. Each of these neurons carries some kind of activation value between 0 and 1, and the connections between these neurons have associated weights and biases, which are ultimately additional parameters with which the model is trained. So the actual means by which this particular model is trained effectively is by using an algorithm called backpropagation. And this backpropagation basically says, okay, so what is our desired output, right? And then what are the combinations of, be it activations, weights, biases, that we can put back as we go back in the algorithm that would then allow us to detect, that would allow us to correctly characterize many of the features or the classification features within the data. The basic structure of any particular neural network is that which looks something like this, where you have an input, you have the hidden layers, which essentially characterize where the learning within the whole network is done, and then the output is where the classification ultimately happens, right? So, I mean, you can imagine you've got images of cats and dogs, and you would essentially throw them into something like this, and the output would tell you whether this image is indeed a cat or is a dog, right? That is really that. And then to take it a step further beyond that, you have convolutional neural networks, which before you get to this portion here, which is they call this the multi-layer perceptron, which ultimately possesses layers which are known to be fully connected, right? You have this precursor stage called the convolutional stage, ultimately, where you use the basic operation of convolution in mathematics to ultimately characterize features within the data. Like, for example, you see there, you have, you're essentially like characterizing this feature of a leg within this zebra, and then you walk all the way through with that particular feature up until you get to these fully connected layers where the classification happens. So what this does essentially is it gives us a lot of those very intricate features that maybe might be lost when we come to this particular stage. Okay, so so in my case, I decided just to use 3 basic convolutional layers for just the feature extraction, and then using only 2 fully connected layers for the classification portion, right? And then the actual data that is used to train the neural network is proper motion data. So the images that I showed before with the globular clusters that had these very nice proper motion, dispersions relative to the background. Those were the images that were used to ultimately train the neural network. So this is just a very, very rudimentary, how can I describe this? Very rudimentary demonstration of the true power that lurks within these algorithms, right? So the left panel here essentially shows just some random selection of data. Serendipitously, this is actually a real cluster. I just didn't know that it was a real cluster. And it is the center of this cluster, as described in the literature, is what I plotted there in red. I'm not sure if you guys see it. But on the other side, what you see is essentially DB-scan detected clusters. So each color represents a different cluster, right? And as you can see in this area that is somewhat dense, what you have is an actual clustering that's been done. So all of these other clusterings, they could be potentially open clusters, or they could be globular clusters. But because I didn't train my model to necessarily incorporate those open clusters, well, they just fall by the wayside, I guess. So moving on from that. And then the second example, so this is just some random selection of data that is within the galactic bulge, as you can see by the galactic longitude between 1 and 2 and the galactic latitude between 0 and 1. So very, very close to essentially the center of the galaxy. And by essentially looking for clusters within this area, and even by plotting the known cluster centers of globular clusters and even open clusters, there are no clusters in this area to be found. But when I applied when I applied DB-scan, that was basically the same story. I found no clusters in this area. Doesn't mean that they're not there. It might just mean that, quite simply, well, they're rare, or maybe even the parameters that I used to ultimately select for these clusters were somewhat off base in this particular instance, or that they're just not there at all. Like there aren't any clusters here at all. So when we put those particular clusters, these obtained clusters, through the neural network, what we find is, so first and foremost, when we train the neural network, what we have is a situation where the accuracies go all the way up to around 80%, which in general is actually quite poor. But that's understandable when you consider that the training sets, which means 150 known globular clusters and 250 just random regions in the background, that's just a very, very small sample of data with which one can actually work with to train a neural network appropriately. But even then, we were still able to achieve these kinds of accuracies. The validation accuracy here, as shown in orange, is basically the how can I put this? When you do classification tasks, what you tend to do is you tend to split your data between your the training set and the testing set, and this was the classification performance of the what do you call this? Of the testing set, right? And what you want in general is for these two lines to track quite closely to one another. Yeah, okay. I'm nearly done, guys. Hang in there. So just to continue from there, when we actually run it through the neural network, what we find is that one big cluster that I talked about earlier, let me just go back, this one big cluster here, which actually corresponds to a real cluster in the data, was the only one that actually survived through the neural network. And then just to show you some of the results from that particular cluster. So if we just isolate those particular points that were obtained by DB-scan, and we look at the proper motion space, what we actually find is this nice, very dense clustering of proper motion values. And these red values here correspond to just the background. So, and then these are just some of the obtained properties that you can optimize for by, or that you can actually improve in terms of their errors by using cone searches, and this is something that has been done in the literature. So in terms of closing remarks, one of the things that I would like to do in future is I would like to basically create like this artificial neural network that also incorporates the differences in the physical properties across actual clusters. So if we know anything about globular and open clusters, is that globular clusters tend to be gravitationally settled, virialized, whereas open clusters are governed more so by n-body physics. So the idea is that if you actually write some kind of neural network that imposes constraints that are linked to those particular governing physics, then you might be able to distinguish between these particular objects. And that's it. Thank you very much for listening to this long-winded talk. Cool.